So we'll talk about scaling VoIP, specifically in the container environment. And in this case, the Kubernetes environment, unlike the raw and build your own bare metal ways. To begin with, we look at containers themselves. Now, how many, surely most of you are familiar with containers generally? Okay, most, maybe not all. So containers in this context, we'll be looking at are primarily designed for operations. So what I mean by that is that, oops, out of order. Containers are not about providing things like speed. They're providing things like surety. That is, we're not trying to optimize the performance of our deployment into the maximum possible speed. We still have virtualization. We're not running a full VM. Yes, it's better than running out of KVM or over a VMware box, but it's not about speed. It's about the surety. It's about being able to deploy this wherever and know that it will work because everything is static. Again, it's not about simplicity. Building out a container-oriented network is often much more complex than just simply deploying it on the computers that you are used to doing so. Instead, what you're building is a common structure that you can use to replicate and go into multiple environments, multiple clouds, multiple bare metal clusters, and have the same set of resources throughout. It's not about expressivity. When you adopt a container-oriented system, you lose a lot of the expressivity. You lose a lot of your ability to tweak little bits, to have this implementation be just a little bit different to better conform to these particular standards. Instead, what you're wanting to move toward is conformity. So we're about constraints in containers. We're not about flexibility. Kubernetes is the tool that we use for managing all of these containers and the structures therein. So Kubernetes ties in all the containers, ties them together into one unified system. It allows you to access those containers by name-oriented means rather than having to use specific IPs that may or may not change. It allows you to disregard state. It abstracts the state from your deployable components, from your artifacts. It handles the scheduling. It handles the restarting failed components. It handles putting the loads wherever you have resources for them to run. It abstracts away the configuration, the specific runtime configurations like the network settings and IP addresses, interconnection. It provides facilities for simple load balancing and scaling of a number of resources, SIP less so among them. And it manages storage so that you don't have any storage localized to your deployments. Ultimately, Kubernetes is your OS in a cluster-oriented world. The idea is to abstract away from the machine, abstract away from the code, abstract away from the installations, and just deal with overall cluster mechanics. VoIP in particular, however, has a number of things that don't quite fit. This is where the out of order tab. So container-oriented systems were really designed for web-based apps. In order to translate container-oriented systems into something that VoIP can use, it's useful to construct an analog of those systems from the web world into the VoIP world. And the two main components we use to do that are constructing the load balancer, which in our case is the proxy, or almost always Camilio in this case, and then worker loads, which are similar to the web servers that you'd have in the web world. And these are the workhorses. These are asterisks, the free switches, the PJSIP stacks, the custom applications that run. Even then, you have some particular things that are more difficult to address in the VoIP world for container-oriented systems. Networking being a huge one. In the web world, you have nice single TCP connections that are through. They don't really care if they're NATed. They don't really care if the IP address changes. They don't really care about much of anything. You can address them by name. Proxies, you can have any number of them. NAT, you can have any number of them. It doesn't matter. RTP is a little more particular. SDP is complicated. And we have a number of ways that we can address that in the container world. But ultimately, you're either going to be running through a proxy or running directly. We have, of course, proxy-oriented methods being the more common approach, using RTP Proxy, RTP engine that everyone's familiar with. And then, of course, we have direct media, which for some reason is a little less familiar in using proxies, but we have the SIP being proxied and the RTP going directly to the machines. SIP, same concepts with regard to the NAT and constructions of known IP addresses, etc. Logging is another issue in the container world because we want to maintain static containers that don't have variable data inside them. So we need to pull logging out from the containers. This is easily facilitated by Kubernetes and others simply by putting all output to standard out. Unfortunately, the default settings of most VoIP components do these to files instead, but there are ways around each of these that we'll cover in the actual implementation. There's some compile time details with Asterisk primarily that don't really have much to do. And then the local storage themselves. So these are things like voicemail storage in prompt storage. Again, in the effort of trying to eliminate any kind of variable and volatile data inside the containers, we pull these out. So none of this is particularly direct until we actually have code to see it. So in this case, what we've done, if any of you were at Astricon a couple of years ago and saw my talk there with the Kubernetes, this code base is very similar, just simply updated. But the idea is to demonstrate how to build a complete VoIP system on top of generic Kubernetes. So in our case right now, we have just a standard Google Cloud Platform Kubernetes installation. Absolutely nothing special about it. We just start a new cluster on the Kubernetes engine and add nodes to it. One minor detail is that in order to facilitate direct IP interaction with my carrier, I wanted to keep stable IPs for the proxies. So in order to do so, I've pulled out the two nodes for Camille. I'm not sure if you can see that, but there's a separate node pool, or in Amazon terms, an auto-scaling group, that's used for the proxies. Should probably make sure, does everyone understand the concept of the proxy, its role in the VoIP installation? I think it's a fairly common idiom generally, but depending on your backgrounds, you may not be directly familiar with it. But the idea is that all of the calls, all of the VoIP transactions come into the cluster via the proxy servers, the Camellia boxes. Nothing goes directly to the internal working machines. So nothing goes directly to Asterisk. Everything goes through a proxy to get inside the cluster. So what we have in these two node pools, we have the Camellia node pool, which is our proxy node pool, separate from the rest of the working node pool. And then we have a high-scale default pool, which contains all of our load. So this allows us to have a small set of external interfacing points so that we can have a more limited set of IPs that we need to register, and then have internal, highly scalable groups that can scale as our load increases or decreases. As far as the cluster itself, it's fairly simple. We have right now 2 Camellia instances, 1 Asterisk instance, 1 application instance, and then a NATS transport for our ARI communication. How we tie them together is, of course, the key. And that's what we look at when we dive into the actual code, the tools for doing this. But let's just start to see how it works. We have, and I apologize, I did not have a carrier that could give me a UK number. So you are welcome to call, but it is a US number. If you call into this cluster, you will get a prompt. Hello. Oops, on that side. We'll miss it. It's a prompt that asks how many replicas you want to run of the Asterisk box. So I'm going to scale it up now to 5. And we see Asterisk is now scaled up to 5. It's creating the containers. After each of those containers comes up, we see the dispatcher list for Camellia being automatically updated and Camellia being reloaded instantaneously via the binRPC. And so now we have instantaneously 2 Camellia boxes and 5 Asterisk instances in, what, about 15 seconds to spin up the rest of those. In the same form, we can call back again.
Hello, please enter your number.
And we'll scale it back down to 1. Dispatcher sets are immediate this time. That's because administratively this is all done by the Kubernetes API. And once they are administratively shut down, the API is updated, and they were shut down as far as the processes a little later on, if you saw. So it's all well and good. It works. But how does it work? That's what we really want to look at here. And there are a number of components in here that let us work in a way that is fairly flexible. So for this talk, I have consolidated a number of tools that we've developed over time to facilitate these things. The 3 major ones here are the NetDiscover, which is cloud agnostic network discovery tool. So it works with bare metal, it works with AWS, it works with Azure, it works with DigitalOcean, it works with GCP, and it's pluggable to extend to any number of other tools. It works very simply both in the command line interface. If you type in netdiscover, it will spit out a JSON output. Again, this is just from a bare metal machine on my desktop. So if you can see that, it just spits out a JSON set which displays the host name, the private IPv4 address, public IPv4 address, private IPv6 if such exists, and public IPv6 addresses for wherever you are. You can explicitly state which value you want. So if we just want the public v4, we can get just the public v4, and it spits it out directly. That way you can pull it directly into, say, an environment variable without any kind of JSON manipulation. This is also available as a Go library, which the tool uses. We bind that in to two more tools. The Asterisk Config, which is a dynamic configuration engine for Asterisk, for templating configurations, specifically in the Kubernetes environment. So among the things this allows you to do is handle the automatic reloading of when IP addresses change. So when we're looking at the set of Camellia boxes, for instance, as these change, Asterisk Config is monitoring with the Kubernetes API the set of Kubernetes instances. And the moment they change, the Asterisk configuration is regenerated for PJSIP, for instance. It doesn't really matter, it could be any module, the entire Asterisk configuration is templated. And you can use these variable substitutions to get at them. But it's monitored, it's automatically regenerated, and it's automatically reloaded whenever anything changes in the network. It allows a layering approach where we have a default configuration set and then a custom configuration set on top of it based from config maps. So in other words, we have a common asterisk image that we statically declare and put up as an artifact. The configuration is all dynamic. So the configuration is applied to the asterisk runtime whenever it is run based on the environment in which it is running at that time. So no configuration is ever bundled into the artifact. The default configuration of this also includes a number of optimizations for Kubernetes, for instance, disabling any file-based logging, and including file-oriented directories for common control structures. It also generates a common set of PJSIP default transports based on the network environment that you're running. So in the cloud environment, this is one of the most important pieces, is that Asterisk needs to know what its IP address is to the outside world or to the world in which it is communicating. So for instance, if you're only communicating to the proxy servers, because in Kubernetes you're frequently single or double natted, you still need to know what address Camellia is going to be talking to Asterisk by. This handles all the setup of the PJSIP transports in order to facilitate that communication. The custom configuration is all templated, like I say. You can source that templated data by a number of pieces, among them environment variables, which are runtime, essentially static pieces of data that you can tie into your containers and have those vary based on the runtime set. Config map entries, so you can map a config map, a secret or a config map in Kubernetes into values that you can use in your Asterisk configuration templates. You can use service data, so any service inside Kubernetes you can link into your templates and pull any arbitrary data from. Same goes for endpoints and network data, as we said. Endpoint IPs is a simple macro. So for instance, you can pull the endpoints of a service, but it's a rather cumbersome set of data. Usually in the VoIP world, you're really only concerned about the IP addresses. So we have a macro endpoint IPs, which just returns the IPs of the endpoints of a particular service. So in our case here, in our PJ-SIP config, let's see if I can get it a little larger. So what we're doing is templating an endpoint, an ARR, an identity, and a set of ACLs in PJ-SIP using the dynamic data from the endpoint IPs of Camelio in the VoIP namespace, iterating contact entries for each of those IPs. So if you've ever done any templating in, say, handlebars, in the web-based things, the Golang templating is very similar. The double braces to indicate template sets. So we have if, we have for loops, we have a few control terms that we can implement, as well as deep inspection of objects, etc. So this is how we have then had a dynamic PJ-SIP configuration based on the set of Camelio instances to which you're communicating. The same kind of thing goes for various other configurations like ARI. We can configure individual users for overlay. We have the extensions, the dial plan. We have individual templates to run, in this case, pull from the environment, the ARI application, which we then feed into Stasis. And you can do this with any of the basic Asterisk configurations. Kubernetes is similar. Kubernetes, always say that. Camelio is similar. We have, in our case here, a configuration template that runs through our system to pull that in with dynamic sets. As we were seeing here, we generate a dispatcher flat file and load that in to have Camelio be able to direct to whatever Asterisk instances there are. All right, the other pieces are less interesting, I think, to the general audience, the ARI proxy for those through. So it's a little bouncy, but that is the set, generally, of what we've done. The bulk, the meat of the data is, as usual with Kubernetes, in the set of manifest files that tell Kubernetes how to run everything in the system. So Asterisk, for instance, we define as a deployment. We start with a single replica. We have a number of containers the configuration of which is very, very simple. We really just have a few environment variables to apply for specific implementations. So for instance, we declare the ARI application, ARI username, password. We declare what cloud for the network namespace, for the network environment. And we start the various ARI pieces. So that's pretty much it. If you have any specific questions with regard to difficulties in the VoIP translation to the container space or in the specific implementation we have here demo, this demo is open source, it's up online. We have the URL there, but it'll be on the slide at the end. So, any questions? Anything specific? Yes?
Are you proxying just the SIP or are you doing an RTP? With Camellia, are you proxying just the SIP or are you also doing a media proxy as well? And
yes, so we can do both. In this example, I'm actually using RTP Proxy for the RTP, so we're proxying the SIP and the RTP. But these tools will work just fine without the RTP proxy, either using RTP engine as a separate component, using RTP proxy, or having the media flow directly to the Asterisk. Any of those setups is common and possible with these configurations.
Okay, thank you.
And so those three default PJ-SIP transports are for the three sets. So one being SIP to internal addresses, media to internal addresses, SIP to...
You said, I think the type was cloud and you use Google Cloud Platform.
Mm-hmm.
We can't unfortunately use cloud platforms from South Africa.
Right.
Can it work on a bare metal Docker host?
Absolutely.
Yeah.
So when I ran it here directly, this same tool is run on my bare metal box. Just don't set a cloud setting and it will fall back to reasonable defaults.
You mentioned NATs in the GitHub repo. What was that used for?
So the ARI proxy. So in order to abstract the ARI applications from the Asterisk instances, what we do is we proxy the ARI connection into NATs. So for each Asterisk instance, there's a NATs gateway running, and that proxies all of the communication onto NATs. So that our applications talk to NATs, ARI talks to NATs, and we have NATs for the common communication signaling channel.
So do you have experience running this setup in a production environment?
Oh, absolutely. Yeah, we have several production environments on AWS, on GCP, and in bare metal Kubernetes clusters.
Okay, and my question would be like on a bare metal, what kind of operating system you use, and are there any like system settings that you need to tune to actually have it ready for production? Like, I don't know, limits, because I'm more like facing couple of troubles, just to say couple of, with the CentOS usually, as opposite to Debian, which is, because CentOS has more limits on it, so to get it with a container.
So for my use case and my preferences, I almost always will prefer CoreOS, so the container Linux. Because it's a really stripped down operating system. It's designed much in the same way as containers. It's a static image that's punched out, separated config, and it's entirely systemd based, and really ultimately it's designed for Kubernetes. You know, it also does a number of things that to get out of the way of, so you don't have any static logs, it's all automatic rotation, journaling. You can set it up very easily with cloud configs, ignition configs, to say, have Docker not dump these endless log files that fill up the disk for long-running processes like an idiot. It generally allows me to template and then automatically boot machines and provision them really easily, and works beautifully in Kubernetes and containers.
I've got a question, Sean. In fact, I've got loads of questions, but I'll just give you one. On the way up, you were scaling the number of workers.
Right.
At what point or how were you checking that they were actually ready for service? Because it looked like you were putting them in dispatcher straight away.
Yeah, so each of the service definitions in, so I cheated. I'm putting them in straight away. Kubernetes does allow you to have arbitrary checks for readiness, both checks for failure and checks for initial readiness. And depending on those checks, it will take it in or out of service. I cheated. I didn't have anything. So yes, right now, it just pops them in whenever they're up. But Kubernetes does facilitate that kind of check.
Okay, cool. So would that work on the way down as well? So we're moving from dispatcher immediately, killing gracefully when there's no channels left on a worker?
Yeah, so that I don't know about, actually. That's a good question. I can't say. Yeah, I don't think so. I don't think there's any kind of readiness check. So like a check to clear before it deletes the pod. Yeah, I don't think there is. You do have control over when the pod ends, so you can do that from your own application glue, but that's not an automated facility, at least to my knowledge.
And one more, if you'll indulge me. Can the workers in one pod be aware of the state of things in another pod?
Oh, absolutely. They have to be. Yeah. I mean, so each of these pods, if we go back to here, each of these entries is a separate pod. So in order to work at all, they have to know about the state and availability of the other pods, or at least the services that are abstracted from those pods. So Camelio has to know about, each Camelio pod has to know about its Asterisk pod.
That's me using the wrong terminology. So if I have a cluster, for want of a better word, I thought in Kubernetes they were called pods, but in London, say, and another one in, say, San Jose, can my Elio in London reflect the state of my Asterisk workers in San Jose if it needs to for a backup config, etc.? Yeah,
it can. So there is what I would call nascent federation support in Kubernetes, where you can federate multiple Kubernetes clusters and get state knowledge between those. I would say it is nascent. I wouldn't put that in production yet. Other people might disagree, but I think I would write my own glue for that. Yeah.
That's great. Thank you. Any more questions? Sean, thank you very much.
Well, surely.